So the basic concept of a radial engine is to create rotary motion from reciprocal motion, which it does by firing pistons in a particular sequence. These pistons are configured in a distinct star shape pattern, which sets it apart from other types of engines. I'm using an electrical motor to drive the shaft, so in our case its function is actually reversed, using rotary motion to push the pistons back and forth, like this. Structurally, the motor shaft is aligned with the main journal center line and is coupled to the crankshaft. Positioned at a radius from this main journal is the rod journal, which holds the master and articulating rod assembly. This eccentric configuration transfers the motor's rotational force through the crankshaft to the master rod and drives the pistons in a reciprocal motion through the cylinders. Additionally, there's a planetary gearbox, and I apologize for the botched animation here. Anyway, you may notice some protrusions along the circumference of the ring gear, and I will talk more about them later. We are now moving into more familiar territory. In this chapter, I wanted to touch upon some of the challenges I encountered while planning certain aspects of this sculpture, particularly the audio. There were a lot of things that were difficult or even impossible to predict, such as electromagnetic interference from the motor, but also more earthly matters which are tied to those protrusions in the ring gear I was talking about earlier. So to keep things as simple as possible and with wiggle room to adapt in case something didn't go to plan further down the line, I once again decided to use the Daisy Seed, which of course for the uninitiated is a digital audio signal processing platform built on the STM32. Initial prototypes used the same radial motion we saw in the previous chapter, but with springs instead of pistons, and the hope was that I could capture the springiness through a transducer and use that as a core element in the soundscape. That didn't work at all, so I pivoted to the idea of capturing the movement in the sculpture with sensors and switches and use it to trigger or influence the sound through rhythmical patterns constructed by the pistons and gearbox. By factoring in the phase difference between the two, I could, for instance, run the resulting signals through a logic gate and thus produce a semi-unpredictable stream of data. Whichever way, the problem was that I couldn't test any ideas without assembling the entire sculpture first, and as you can judge by the length of this video, I was not going to go through all that work for an idea that just maybe would work. So I decided to push the problem further down the line, and consequently, this is the first sculpture I've ever made without having a single tangible clue as to how it might sound until the very end. The mechanisms and components in this design are both deceptively simple and intricately complex at the same time. Conceptually, understanding what causes the various motions to occur is relatively straightforward, but the details that make them operate in a manner I'll confine myself to describe as relatively smoothly present an entirely different challenge. The central mechanism, as presented in Chapter 1, consists of 37 different parts, including bearings but excluding fasteners and cylinders. Most of these parts must be manufactured to a tight tolerance to ensure concentricity along the crankshaft as well as minimize backlash in the gearbox, and somehow this task was allocated to my 300-watt desktop CNC router. Cast acrylic, which brings forth a new consideration regarding dimensional accuracy due to varying thickness across the same sheet, is of course a very malleable material with this machine, but things will literally heat up in the next chapter. More on that later. The planetary gearbox, which I'm working on in the background, consists of 3 gears, namely the drive gear, carrier gear and the ring gear. The ratios between these gears are inconsequential to the gearbox's function and exist only to reduce the rotational speed of the ring gear compared to the crankshaft. As I briefly mentioned in the second chapter on musical ideas, I wanted to explore the possibilities of using phase differences as part of the compositional method, and this ultimately is achieved in the gearbox regardless of the insouciant approach to its ratios. In a real radial engine, the gearbox controls the timing for opening and closing the valves that drive the pistons, which sounds pretty important, but in our case, as I said, it's only a matter of achieving 2 cyclical motions at different speeds. For the sake of rigidity, aluminium was the material of choice for the chassis and other components that required a certain stiffness, such as the crankshaft and rod assembly. I was quite concerned whether I would be able to pull it off or not, and as you can hear, I was not in for a good time. Thankfully, PCBWay reached out and wanted to sponsor my project, so I sent them the design files for the parts that I hadn't already made myself, and I think it was about 12 different parts altogether, most of them pertaining to the chassis and parts that were difficult to make at home. They also sent me a couple of gadgets, such as these PCB rulers. The whole process was very simple, and you can choose between a lot of different materials and finishes. There are also options for extra tight tolerances and inspection reports. This is brushed aluminium, while this one is bead blasted and anodized. Looks gorgeous. Everything was exactly to the required dimensions as well, so massive thanks to PCBWay for helping out. I don't think I would have been able to finish the project without them, so go check them out. I highly recommend their services. Link in description below. Back to my own, less auspicious CNC service. As I drudged on, I was able to tune my settings to something resembling a router more than a tumble dryer and churn out the remaining pieces that weren't outsourced. I think I ended up using a 3.5mm 2-flute bit at 500mm per minute and 10,000 RPM with a cutting depth of 0.2mm. If I were to do it again, I think I would have gone even shallower on the roughing passes whenever the entire width of the bit was engaged in the material, but we were already looking at an hour of runtime for each part at this point, so I wasn't too keen on prolonging that. Anyway, to make the best out of a bad situation, I went over the parts with sandpaper and it turned out okay. Just a quick note on tapping. Big surprise, there is actually a big difference between all the various tap types, which I found out while doing this. So if you are repulsed by the discontinuity in tool usage in this particular sequence of shots, then that's why. Anyway, out of the 67 holes, I only broke one tap, which I'm mildly chuffed about. It was literally on the last hole, and it put me back about €20. I'm going to take you on a bit of a bogus journey now. What I'm about to show you is the same approach I ultimately ended up going with, but with a different part design. So it's not exactly a dead end, but we'll get to that in a minute. For the Pistons, I wanted to use a different material than the rest of the sculpture. As you remember from the first chapter, the Pistons are supposed to slide back and forth within the cylinders, so I needed them to be light and soft. I had a piece of pine in the basement, which I decided to run some tests on. Each piston, at least at this point in our story, consists of 4 parts: the main circular body, a wrist pin that connects to the rod, and 2 mounts that hold the wrist pin in place. There's also a bearing which helps the piston swivel freely around the rod. These parts are mostly press fit together, but I also made a gluing jig to fasten the circular body to the rest of the assembly. Now for the problems. Pine has a coarse grain because of its fast growth rate, which makes it less suited for fine woodworking, so what I found was that the circles, which were supposed to be perfect, came out a bit oblong and didn't work very well in the cylinders. That was not the only problem though. Because of the minimal lateral surface area, the pistons would wobble at the end of each cycle, creating unnecessary resistance for the motor. I quickly realized that something had to be done, either by installing guide rails in each cylinder to keep the pistons on a straight trajectory, or to simply add more length to each piston, which is what I ended up doing by 3D printing them with this beautiful linden wood filament from Prussia. So much for material purism. Delving further into the audio aspect of this work, I wanted to talk about my solution to the audio conundrum presented in Chapter 2. As you may recall, I decided to employ a wait-and-see policy to the relationship between movement and sound, and the framework for this policy was to position 10 rolling switches around the circumference of the planetary gearbox, which at regular intervals would collide with protrusions in the ring gear. While I initially had planned to use these as a sequencer, I found that it all became very predictable due to the cyclical nature of the sculpture. At a stage in the future from where we are at this point in the video, I also realized that the mechanisms were loud enough on their own to be an integral part of the overall soundscape without amplification, and also already behaved like a sequencer, making a second one redundant. It was all a little bit static and led me to look for ways to increase entropy while not straying too far from the machine aesthetic already present. In the end, the sound I chose to pursue was achieved by using the stepping frequency of the motor as a fundamental frequency in an array of overtones which were triggered randomly by the aforementioned switches. So regardless of the speed of the motor, the digitally created audio would always be in tune with the machinery, and while the exact note triggered by each switch remained random, it would always stay within a cohesive cluster that would be difficult to describe as anything else than one sound. While using drones in my soundscapes is something I generally would avoid, I also appreciate that it has its use cases. I did play around with some of my more typical melodic real-time composition algorithms for this sculpture, but it felt out of place both sonically and conceptually, considering the periodic character of the sculpture as a whole. As we are working on the user interface in the background, I Thought I should mention that this sculpture is powered by an 18-volt 3.33 amp external power supply. The motor is running on 12 volts, while the voltage through the switches and LEDs is 3.3 volts. The audio amplifier is the only component using the full 18 volts, while the other voltages are regulated with buck converters. The amplifier is a Class D TPA 3110, and I'm using a Dayton ND65 speaker with a matching passive radiator. On the user interface we also have an on-off switch, a volume knob and a 1/4-inch stereo line output. A quick note on the LEDs: the common pins on the switches are connected to 3.3 volts, while the normally open ones are connected to a designated input pin on the DAISY, as well as the A node of its corresponding LED. At some point during the breadboarding stage, before I included the 3.3 volt regulator, I actually used the LED's forward voltage drop to regulate the original 12 volts I sent through the switches to interface with the microcontroller. I was a little concerned that I would fry the inputs if any LEDs failed, so that's why I went with the 3.3 volt option. We have finally reached the stage where I will put all of this together. There is no sensible way of evenly spreading information across the 10 or so minutes of this chapter, so I'm just going to present it all in one piece. The chassis consists of 5 pentagonal brackets held together by threaded rods. 3 of these brackets are mounted to a bottom plate, while 5 pieces of acrylic, which also act as mounts for the electronics, help solidify the structure even further. The speaker enclosure, which is an 80mm diameter acrylic tube, is attached to the rear bracket with cables running through extremely tight holes to make the enclosure as airtight as possible for maximum passive radiator efficiency. I don't expect anyone to sit through this entire chapter, so feel free to skip around and use it as a reference for the parts of the construction process that interest you the most. That's all I have to say, I think. The Fusion design files and schematics are up on my Patreon page for those of you who are interested in that, and if you have any other questions, leave a comment down below. Thanks for watching.
you.